The moon is a harsh, airless vacuum with no liquid water and no oxygen, yet it manages to consume metal equipment at an alarming rate. For decades, space agencies have observed a baffling phenomenon where high-strength alloys sent to the lunar surface return or remain pitted, thinned, and structurally weakened. While we associate corrosion on Earth with moisture and oxidation, the moon utilizes a far more aggressive mechanism: aggressive physical abrasion combined with rare, extreme chemical anomalies. The primary culprit is lunar regolith, or moon soil. Unlike Earth soil, which is softened by biological processes and water erosion, lunar regolith is composed of jagged rock fragments, glass shards, and metallic particles created by billions of years of meteorite impacts. Without an atmosphere to weather them down, these particles remain as sharp as industrial diamonds. Under a microscope, every grain resembles a tiny shard of broken glass or a serrated blade. This lunar dust possesses three lethal characteristics that break down metal defenses. First is its extreme sharpness, which acts like high-grade sandpaper against any moving part. Second is its powerful electrostatic charge. Constantly bombarded by solar winds, the dust becomes sticky, clinging to metal surfaces and resisting all attempts to be brushed away. Third is its strong reducing environment. On Earth, metals form a protective oxide layer that prevents deep corrosion, but the hydrogen-rich solar winds on the moon strip away these armor layers, leaving raw metal exposed to constant friction. The damage is primarily physical rather than chemical. Scientists refer to this as erosive wear. During the Apollo missions, astronauts reported that their spacesuit boots were worn through after only a few hours of walking. Even more shocking was the effect on the Apollo lunar module's titanium engine nozzles. After only a few days of exposure, the metal thickness decreased by 30%, covered in microscopic craters that reduced its tensile strength by nearly one-third. Recent research, including samples brought back by the Chang'e missions and studies from Jilin University, shows that even the most durable materials struggle. Aluminum alloys lose 40 to 60% of their fatigue life on the moon, while the friction coefficient for stainless steel nearly doubles. When lunar dust enters the gears or seals of a machine, it acts like microspace piranhas, grinding the internal structures until the device fails. However, a small percentage of the damage is indeed chemical, occurring under three specific, eerie conditions. First, the intense heat of meteorite impacts, reaching over 3,000 degrees Celsius, can create localized environments where iron minerals transform into hematite, essentially rusting in an instant. Second, research from the Macau University of Science and Technology suggests that Earth's own magnetic field leaks oxygen ions toward the moon during certain orbital phases, allowing for slow oxidation in the lunar polar regions. Finally, the extreme temperature swings, ranging from 130 degrees Celsius in the sun to negative 180 degrees in the shade, act as a catalyst for slow-motion chemical decay. These discoveries have forced engineers to rethink how we build for the stars. As humanity prepares for permanent lunar bases, the focus has shifted from chemical rust-proofing to advanced abrasion resistance. To survive the moon, future equipment must be shielded by specialized coatings or completely sealed away from the black attribute of lunar soil. The moon remains a treasure trove of clean energy like helium-3, but to claim it, we must first learn to withstand a world that literally grinds our greatest inventions to dust.